Perhaps you have heard about using molten salt baths for fast, low-cost annealing of cartridge cases. Well then, join us for this video series as we take an R&D look at this topic and share our progress and insights. We call this the PounderBath project. This is the first of 3 videos where we introduce you to the ideas of using molten salt baths for annealing. To get started, we review some of the basics of brass cartridge cases, look at hardness and annealing in general, discuss neck failures, and explain baselining and how to use it. Brass has been used for cartridge cases since the 1800s. It was found over time that a ratio of 70% copper and 30% zinc made an ideal alloy for cases. This alloy is referred to technically as C26000 or 260 brass. It's commonly known in the industry simply as cartridge brass. The cartridge case is the ammunition component that holds everything together, but it's much more than that and is a critical part of the loaded round and overall shop performance. From the standpoint of annealing, there are 2 basic styles of cases. There is a limited need to anneal straight wall cases. A couple of examples would be reforming 223 Remington into 300 blackout and high performance 4570 rounds. However, for bottleneck cartridges, annealing is very important, is what we focused on in this study. When we look at the cartridge case, which is what we just call brass, it all looks the same. But metallurgically, there are 3 important hardness regions. The head, which is the hardest, the body, the middle part, which has intermediate hardness, and the neck and shoulder, which are the softest. In the process of seating a bullet, the bullet deforms the neck brass by pushing it out radially. This radial deformation causes a hoop stress in the brass. This stress is just balanced by the pressure the bullet exerts against the case and holds the bullet in place. When the round is fired, the dramatic increase in pressure within the case drives the brass against the chamber, temporarily deforming it, a process we call obturation. As the pressure decreases, the case returns roughly to its pre-fired condition, thus allowing extraction. However, the case is now plastically deformed and needs to be resized before being loaded again. How cold work a case is and how much deformation has occurred are important issues in annealing and resizing. So concerning bullet seating and round performance, the hardness of the brass, the neck, and several other factors are critical and should be measured and controlled as precisely as possible. Let's take a closer look at each of the individual hardness regions in the brass. For reference, we've included this cross-section of the 223 Remington case from ammunition making by Frost. Quick footnote. Today, the diamond point hardness in this diagram is referred to as Vickers hardness with the symbol HV. The head and associated webbing have the highest hardness value. This is because they have to hold up to maximum chamber pressures and bolt thrusts coming from firing a round. The head is not resized and should not be annealed in any way. The body needs to maintain intermediate hardness, displaying a certain amount of springiness. So after it operates to the chamber wall, it will recover enough to allow easy extraction. With full-length resizing, the body returns back to its original dimensions. Resizing the body also cold works the brass, and this region should be part of the annealing profile. Alternately, for those who want to fireform their cases to the specific firearm, the body isn't resized, but annealing is still needed to help maintain the springiness of the brass. For most bottleneck cartridges, the shoulder head spaces the case and is important for chamber clearance when loading the round. Whether full-length resizing or fireforming, the shoulder needs to be bumped back and needs to be in the annealing profile. The neck must accept the seating of the bullet without cracking and is responsible for holding the bullet in place. This is the region where careful attention to annealing is needed. You can see from the diagram that coming off the shoulder, the hardness should be between 85 and 115 HV. The folks at Annealing Made Perfect, AMP for short, have studied this extensively and from their own research and analyzing new cases from Peterson, Lapua, Norma, concluded a hardness range from 95 to 100 HV for the neck is ideal. You can see there's a balancing act between cold working and annealing that is needed for safety reasons, proper functioning of the firearm, the longevity of the case, as well as enhancing the performance of the loaded round. We can group neck failures into two categories. The first type of failure are cracks in the neck. The most common cracking comes from the normal process of reloading and firing a round. We call this cold work process cracking. Here's a few examples of cracks in 223 Remington that you'll see. These two show cracks in the neck that appear when the rounds are fired. These types of cracks are pretty easy to spot, and the case is finished and should be discarded. Here's an example of a small crack that got started as a process of full-length resizing. These can be pretty small to begin with, but as you trim or deburr the case, you might feel a snag, and this is an indication you've got a crack. Here's a crack that didn't appear until we went to seat the bullet. This happens after a lot of work. It has gone into preparing the case, priming and charging, and attempting to seat the bullet. Unfortunately, all for naught. The second type of cracking is stress corrosion cracking, SCC for short. In this case, the crack in the neck just appears. With today's ammunition and components, SCC isn't very common, but it does have a very interesting history. In the 1800s, rifle ammunition used by the British Army in the Indian subcontinent was stored in horse stables during the monsoon season. When they retrieved the ammo, they saw the neck cracks had just appeared. It wasn't until 1921 that scientists identified what was happening. It turns out the high concentration of ammonia that came from the horse pee in the stable, combined with the very humid weather in the monsoon season, causing the copper and the brass to weaken, and the stress in the neck of the cartridges created cracks, thus the name season cracking. This led to the universal practice of annealing cartridge cases, and though for commercial ammunition the discoloration caused by annealing is removed, you'll see on military ammo the discoloration is left in place, perhaps to assure the Army that the cases are actually indeed annealed and won't season crack. The other type of failure that can occur is from over-annealing. It's hard to know that this type of failure is going on because it's entirely metallurgical. Improper annealing by adding too much heat, heating too long, or heating incorrectly can lead to poor neck tension and poor performance of the case, shoulder, and body. And if you really cook the brass, it's possible to soften the case head and webbing, and this could lead to catastrophic failure. We wouldn't presume to instruct legions of reloaders on how to prepare cartridge cases, but we wanted to present what we do to illustrate a few key ideas. We think of case preparation, indeed loading the entire round, as a process workflow broken down into individual steps, as shown in this diagram. To keep things simple, we show only the key process steps, but all the steps are important. The little donut-shaped affairs for each of these steps symbolizes the vicious circles that we do over and over when preparing cases. First, we want to convey that we understand how to properly prepare cases. The reason this is important is later in this presentation and in future videos, we will be presenting analytical results which may be surprising and only revealed by carefully following these steps. Secondly, we want to convey the idea of baselining. This is simply going through the process to return an item, in this case cartridge brass, back to a stable known condition by controlling all the key factors affecting performance. So if you will, starting from the same baseline. And here we're trying to return the cartridge case to as new condition. Finally, show where we think annealing fits into this process. As we previously explained, Resizing cold works to brass. We suggest annealing after cleaning improves establishing the best baseline. So when resizing the brass, we have reproducible metallurgical as well as dimensional conditions. What are the benefits of adopting a baseline approach? We feel you can be assured that all the vendors providing reloading guides are starting with new, properly annealed cases. Using baseline with the processes we showed on the last slide is an excellent way of returning fired brass to its original condition. This gives us the best chance of reproducing the results the vendors provide in the reloading tables. Another benefit is better understanding what variables are important and how to control them to achieve the best performance. As we work through the process flow consistently, we gain confidence in the various steps and minimize the confounding effects of not controlling key variables. For example, here in PounderLabs, we first deprime, then ultrasonically clean all cases. This way we remove all traces of combustion products and don't have to rationalize having combustion products that might affect the overall quality of the reloaded round. Some suggest that the combustion products don't affect annealing, and others claim it lubricates the seating of the bullet. The bottom line is, by not baselining the brass back to as new, we have to try to explain away or in some way discount having the combustion products in the case. This means we've lost control of potentially important factors. Once we have the various factors under control, we start to better understand which are the most sensitive and can be on guard for making sure we control those well. This all goes to contribute to a better product, whether you look at just preparing the case or you're thinking about it as the entire finished round. Let's illustrate the benefit of baselining by reloading some 6.5 Creedmoor rounds. After we prepared the cases in the way described earlier, we loaded rounds with different charge levels using reference data provided by Sierra. The Sierra loading table was chosen because it aligned well with components we had on hand, and the Savage bolt gun we have available was a good match for the Sierra specification. We're using the Pounder Z5X group buy method for the experimental design. We have a separate video available on the PounderLabs YouTube channel if you're interested in learning more about Pounder Z. A single star means we have an exact match to the Sierra table. Those with a double star we feel are close enough to use for this example, since we're primarily just focused on internal ballistics. We're loading 140 grain Hornady bow-tail hollow point using reloader 15. We're using once-fired Hornady cases. We're using the Winchester large rifle primers. Here's our trim and our cartridge overall length. You'll see a small difference here because we're using Hornady bullets instead of Sierra. But again, since we're looking at internal ballistics and not really commenting about how the bullet flies, we don't think we have a big problem here. For the Savage Model 10, 24-inch barrel, 1 1/8 twist. And we're going to be 100 yards bench rest on an internal range using bipod and rear sandbag, so we're taking wind out of the equation. As usual, we're using the lab radar, weather meter, weather flow weather meter using Excel and the on-target TDS software. Here's the result of our shooting experiment. The x-axis is charge weight in grains. The left-hand axis is muzzle velocity in feet per second from the lab radar. The right-hand axis is standard error of the mean for the velocities, but we won't go into detail at this time. The red diamonds are the charge weights velocities from the Sierra table. The blue circles are the average of the 5 shot groups for the charge levels we loaded. The dotted line is the first order regression for our groups, and the loading equation is here. Notice the coefficient of determination, r squared, is very close to 1, suggesting we have a very good fit of the data to this linear equation, which, as you can see from the plot, aligns very well with the Sierra data. What this means is by using baselining, we're able to replicate the data from Sierra, and even more, we now have an equation that we can use to calculate any velocity we want based on charge weight within the load range. Now the next step would be to build charge weights to optimize external ballistics, perhaps selecting charge weights to understand barrel harmonics, or choose a load that bucks the wind for long-range shooting. The takeaways are this. By using baseline, we can improve our reloads, develop equations for predicting velocity based on charge weights, more closely match public load data from the vendors, and all this leads to faster, more efficient solutions for reloading and improve reproducibility. This completes our presentation, and as you're thinking about subscribing, please take a moment to look over these important notes and disclaimers. They're here for both your protection and for ours. Join us for our next video in this series. Thanks for watching. See you soon.